very basic H nu, and it depends on the efficiency of the amplifier. Then added to that, of course, is the total energy in the transmitters and receivers, which depends on the power in the encoder, the decoder, and the transmitter and receiver divided by the bit rate. And what I'm going to do now is just give you some numbers, give you an indication of where these energies fall and compare them with that top-down analysis that I did before. Oh, and before I do that, I need to say that the optical transmitter is quite a complicated beast these days, and there's a move, as I'll explain in a few minutes, to more advanced modulation formats, QAM and other higher level QAM modulation formats, and optical transmitters require usually a multiplexer to take data at lower bit rates, to drive a series of drivers, and as you get to higher and higher levels of modulation with more advanced modulation techniques, you tend to need cascades of modulators, or modulators with many ports on them, and each of these modulators is typically driven by a driver into a characteristic impedance that matches the signal. And you might say, why is this guy talking about characteristic impedances and drivers in a talk as fundamental as power in optical transmission? It turns out that the power required to feed the modulator can become a very significant part of the total minimum energy consumption in the network. So this Z mod, which is the characteristic impedance of the driver, of the modulator driven by the driver, typically is either capacitive or a 50 ohm load. And there are energies that are required to either charge a capacitor or to put a voltage across a 50 ohm resistor. And this can turn out to be significant. This energy in the modulators is significant when it comes to higher order modulation formats where quite a large number of drivers and ports on the modulator are required. And I'll come back to that. So here are the key numbers. This is the total amplifier energy E-amp. That's that first of those equations I showed before, the fundamental limit on energy consumption required by the amplifiers as a function of the amplifier spacing for different modulation formats, on-off keying, BPSK. This is assuming a 2,000 kilometre reach from input to output and a 100% efficient amplifier, which is of course very optimistic. And you can see we're talking about something less than, this is a picojoule per bit, so everything's less than a picojoule, maybe 10 to the minus 13 joules around here for 100 kilometres. So in fact the energy, the minimum energy you could ever use for transporting a bit of data between 2 points over optical amplifiers is very small. It's almost insignificant in the picture here. Although if you end up with an amplifier which is not very efficient, this can boost up to higher levels. The very smallest energy consumption you could probably get in an amplifier transmitter-receiver pair, and this is a lower limit, remember, not what you can do today, is on the order of about a picojoule per bit. So this grey area is meant to represent a broad area where the transmitter-receiver might lie. So at the fundamental level, if you go down to the very minimum energy, it's the transmitter and receiver that dominates. And so that's where we need to probably concentrate our efforts in getting the energy down to the bare minimum. This is a Shannon bound, and I'll come back to that in the next slide. It's really quite low. If you get very close to the Shannon limit, then the minimum energy required for transport through the amplifiers is really very tiny. So this is the Shannon limit, which relates the signal-to-noise ratio per bit to the spectral efficiency. Now, I want to take you back to that first equation. You might remember that first equation, the minimum energy per bit depended on the signal-to-noise ratio. So there's a direct relationship between the minimum energy to transport data and the signal-to-noise ratio. And this gives us the signal-to-noise ratio as a function of the spectral efficiency. So this axis here could either be energy per bit in this direction, or efficiency, which is the inverse of the energy per bit, in that direction. So if you want to improve the efficiency, you need to move in this direction here. So BPSK is in fact slightly more efficient than on-off keying because it operates at a lower signal-to-noise ratio. One could, in principle, move down to this region here if you had some extra error-correcting coding. You could get close to that limit by lots of forward error coding. But the problem is that if you move in this direction while you'll gain in efficiency at the level of the amplifiers, you will require increased CMOS processing power to do the coding and decoding. So an open research question here is, where is the optimum point along this line where the increase in CMOS coding and decoding energy is balanced by the improvement that you get in the efficiency due to this earlier equation. Now, as I said before, there is a move in the optical communications world to higher, more advanced modulation formats in an attempt to move to higher spectral efficiency, because higher spectral efficiencies will ultimately improve the amount of data that we can put through a single fibre, and there is a growing pressure on the capabilities of the existing fibres. So what happens if we consider going to a high-level modulation format? How does that affect the energy efficiency? Well, it turns out it's not necessarily good news, because typically the higher level modulation formats, QAM, 16 QAM, 64 QAM and so on, are in this region here. In fact, typically off the scale with required signal-to-noise ratios of something like 25 dB or more, so that in order to get to this region where the spectral efficiency is high, one needs quite a high signal-to-noise ratio, and therefore the energy per bit increases. So advanced modulation formats increase the signal-to-noise ratio, and in addition to that, as I mentioned earlier, as you go to higher, more advanced modulation formats, you require modulators with more ports on them, and there's more energy consumed in the transmitter and receiver. So this is also an open research question, and one that I know a number of groups around the world are thinking about. What is the optimum spectral efficiency to use? What is the trade-off between spectral efficiency and energy consumption in a network using advanced modulation formats? I don't think anyone has the full answer to that yet. So putting into context what I've just said, here is this data from the historical data of energy per bit from undersea cable systems. And this is sort of the broad area where that bottom-up analysis that I just did comes out. And this is meant to be an approximately equal to sign. There is about 3 orders of magnitude difference between the current trends of the best commercial equipment and this minimum bottom-up analysis based on real modulation formats, which is not as good as the Shannon limit. The Shannon limit's somewhat below that. So there is a factor of 3 improvement here potentially available in this energy efficiency. Now, why is there a difference? And the reason has to do with the fact that if you buy a piece of commercial equipment, there's lots of other stuff in the box in addition to that little modulator and the driver that I showed you. In fact, you can think of it like this. Here is a key function which uses a minimum energy. This might be an amplifier, an optical amplifier that uses a minimum amount of, which can be, you can define a minimum theoretical limit for that. But there are lots of losses and inefficiencies, such as system penalties, system margins, and the pump laser efficiency. Pump lasers in optical amplifiers are typically a few percent. And these things all cause a multiplication factor here, so that the actual energy required to drive this device through all the losses is significantly larger than this one here. In addition to that, there are various overhead functions that take power and energy from the device. Things like monitoring and supervisory circuits in the amplifier, which are actually independent of the power required here. So there's a proportional component and an overhead component. And these all add up to mean that the total energy required is considerably more than that minimum that I talked about. And typically this ratio between the minimum energy required and the actual energy required is of the order of 10 to the 10 to the minus 2 to 10 to the minus 4. So a key conclusion here is that minimising this E minimum, trying to work out ways to juggle that theoretical limit, is not necessarily the best strategy for minimising this total. And really what we need to do is focus on the losses and inefficiencies in these various overhead functions. And that's a way that we can make good progress in reducing energy consumption. Now I'd like to move on to networks. This is a very difficult subject from a theoretical point of view, and there's no, as far as I know, there's no good theory out there that can tell us what the energy required is for some kind of switch network. There's just no theory available for ultimate limits on energy required to switch data in a network. So here is an attempt to make sort of a rough stab at the amount of energy that you might require in the best possible scenario. So this little model has a number of user ports and an access network, which I'm going to ignore for now, and a series of switches and transport systems. And the idea is that then any port from any user on an access network can connect to any other user. And in general, we need a network, a switch network, that can provide a connection from any one user to any other user. Not necessarily a permanent circuit switch connection, maybe a packet switch connection, but some kind of connection between them. So one way of getting a stab at the minimum energy required for the network would be to think about what kind of bare minimum switching network you'd require in able to get a connection from one input to some other output. And this is a little model of that. Now, we've gone one step further than that and actually done some modelling of a basic network like this based on some real technologies, and I'll give you some numbers in a moment. But the idea here is we have input ports, and N user is the number of ports. This, in today's network, would be 1.6 billion and growing. And with the Internet of Things, it's going to be, what was it, 10 billion or 20 billion or something. Usually this operates at a lower bit rate, and there's usually some kind of aggregation which has a large number of input ports and a fewer number of output ports, which then multiplexes up to a higher bit rate for use in the core. So this is a very simple model with a lower bit rate access, a higher bit rate core, some aggregation switches, and then switches throughout the network. And what I've done is a very simple modelling of all these switches using some existing technologies and looking at the lower limit you can get for those technologies, and then putting the lot together to work out sort of some fundamental limit on network energy. And these are the numbers used in that model. We've modelled all optical devices. This stands for optical, which would use switches such as semiconductor optical amplifier gate arrays, or devices that have electro-optic switches, either lumped or travelling wave electro-optic switches, or electrical to optical to electrical switches, such as wavelength routed switches with electronic driven wavelength converters, and CMOS devices. However, one must take into account the fact that CMOS switches or electronic switches require optical to electrical conversions before you do the switching. So in fact these blue areas here represent the O to E converters and demuxes and muxes you require if you're using electronic switching. So this sort of encapsulates a variety of optical switching technologies and electronic switching, and these are the numbers that are used in the analysis. I won't go through them all here, but these are numbers based on the best available technology, or at least some estimate of the lower limit one could expect to get. And with that, we can put together this entire picture. And this picture sort of summarises this whole talk. This shows the network energy per bit. That is the energy required to get a bit from one input port to the network to an output port of the network. And that network has 1.6 billion users here in 2010. The top curves are the current trends. This is what I talked about in the first part of the talk, and I was really describing 2020 and I projected out to 2010 and I projected out to 2020. These are the same data that I showed then. And these are the data based on the the lower bounds that I used using the fundamental limits. This is for switches and this is for transport here, and these are the lower bounds, these are the current trends.